Hey, welcome you all to Kafka tier storage session. I'm Satish. I'm engineering lead in core data team at Uber. I'm Apache Kafka contributor and Apache Storm committer in PMC.
I work as data architect at Uber. I work closely with Satish and Kafka team. I'm also an Apache Kafka committer and PMC. Today we're going to talk about Kafka tier storage. Before we go into the architecture, design, and all the interesting details of Kafka tier storage, I'll just give an introduction of how Kafka is used at Uber. Uber is by nature real-time business, and Kafka powers most of it all. And it is one of the critical pieces of infrastructure that we run at Uber. As you can see from this image, the data that flows from driver apps are, for example, Uber Eats and all of our API services all flows through Kafka. And then we have application databases such as MySQL, Schemaless. These are our online databases when the user or application sending any events that lands into our real-time online DBs. From there, we run a ingestion pipelines that lands into Kafka, eventually lands into Hadoop for further analysis. The most interesting part of this is the real-time nature of this. That is, like example could be if you order any food, we're calculating ETA based on a lot of events around the restaurants in that area. All of that powers through Kafka, eventually in Flink, and giving that data back to the app itself. Similarly, when you take a ride and complete the ride, the payments processing happens through the Kafka as well. So Kafka, the availability of Kafka and the reliability of Kafka extremely critical to Uber as a business and to our users. So with that in mind, going to the next slide, can you go to the next slide? So this is kind of gives you kind of overall footprint of what we do at Uber in Kafka. We have around 5 trillion messages per day that's flowing through our Kafka infrastructure, around 3 petabytes per day. We have in total 2,000 plus nodes that is running in our production. All these 2,000 nodes are divided into multi-clusters. So each cluster has different use cases, different configuration, depending on applications and services that are using that. And we host all of these nodes on-prem in our data centers. And all of these nodes are right now running around 40 terabytes of disk, around 20 disks. Each of them are 2 terabytes arranged in RAID 0. And given the scale of these clusters, a node going down is a regular occurrence for us because of the nature of the disk and everything else and the lifetime of the hardware itself. So whenever the node goes down, we don't want to run the online replication because we have pretty much all our nodes are around 80%, 70 to 80% full. That comes around like 28 terabytes, 30 terabytes of data, each of the node hosting. So if a node goes down, if you bring it up and trying to replicate the data through the online replication, it will affect our producer latencies. As we looked at in the previous slide, the real-time nature, the latencies are extremely critical to all of these services. Our latency guarantees all the way from 20 ms to 100 ms. That is our guarantee that we give our internal services, internal customers. So for us to maintain the produce latency is extremely critical. So we don't want to kind of compromise that by bringing the online replication. So what we did is an after replication, which uses rsyncs to copy the data from all the lead and nodes for the topic partitions that is hosted on a node that went down. So when the node comes up, we don't start the Kafka broker immediately. We run the after replications and get most of the data. And last segment data, for that we bring up the node and consume rest of the data. So this works fine, but this is again cumbersome. It takes time. Depending on the size of the cluster, it could be anywhere between 6 to 8 hours or more than that. So imagine in a case of where you ship all of this data into, let's say, Hadoop or S3 or GCS, and you're only hosting the data, recent amount of data. So that way, when the new node comes up, we only need to sync the latest data, not all of the data. That's one of the operational improvements that we are looking at when we are looking into Kafka tier storage. The other most important thing is most of our consumers, when they are reading the data, they are actually reading the latest data. Only in case of failures in the consumer applications, maybe an outage or whatnot, they want to go back and backfill the data. It happens so rarely. When we check the discrete times on the consumer side, it only happened 2% of the time. So do we really need to host all of our data into the local disk? Can we ship this data into HDFS cheapest a cheaper storage and keep our local storage much more tighter and much more smaller. There are several benefits to it. You have data that is available. You can, as we talked about, a node going down doesn't really impact. We ran few tests when a node goes down, bringing back up with this data shipped to HDFS or remote storage. We could bring up a new node within 10 minutes because it doesn't have a lot of data to sync. So the idea behind Kafka tier storage born out of that, and there are a lot more interesting use cases that we can actually think about as we go along in the future. As we talked about in the earlier slide, we are actually taking the online data, online DB data, going through the ingestion, landing into Hadoop. Can we actually take this data and land it into Hadoop and make it much more interesting to read directly from the Hadoop rather than talking to Kafka itself, so that you can have an offline process that can take the real-time data that is getting produced to Kafka and actually eventually realize into Hive or Presto. So the goals behind this is scalability, improving the scalability and the number of partitions that we can host on a single broker. Again, number of topics kind of limited to the amount of data storage you have on a typical node, right? So if your partition is around 300 gigs, the number of partitions you can host typically on a single host on a 30 terabyte disk is 1,000. So when you actually cut that down into much more smaller by shipping the data into remote storage, you can increase the number of partitions that can be hosted on a single broker. And efficiency, as I said, talked about earlier, how we can actually reduce the hardware cost as well. That is, you don't need to have a huge disk running around this, and actually execute that much more cost efficient and much more performant. And the ability of elasticity, scaling out the cluster is much more doable with the data that is shipped to remote storage rather than everything within Kafka. So what are some of the non-goals? What we are not really promising here right now? So in this version, we're not going to support the compact topic set, and it doesn't support the JBOD. And tier storage in no way means of replacing ETL pipelines at all. ETL pipelines has a whole set of story around that. We are not going to, this particular feature is not going to replace that at all. So that's the kind of background of what and how the Kafka operates at Uber and why we actually started the Kafka tier storage project. So some of the features that we go much more deeper in here is providing storage layer beyond local disk, right? So we have page cache where the data getting kind of written as read and eventually get synced to the disk itself. And with the tier storage, we can have a storage support to S3, Azure, GTS, and similarly HDFS. We talked about improving the operational efficiency. That is like a node going down, bringing that up doesn't take hours. Cost efficiency, we do not need to have huge disks that we need to attach to our hardware. We can actually string that and possibly use an SSD in a much more cost-effective manner, and also increase the performance of those brokers itself. And isolation of reading the latest and old data. Again, our bet is that for the most part, everyone is in a healthy services. They are reading the latest log segments, not going and back and reading the old data. That happens very infrequently. And with that, you can actually optimize for the latest reads, and old data can be read slowly, which is okay when you're doing a backfills. And the tuning and provision of clusters. Now, when you have the data that is shipping to remote storage, it's much more easier to kind of expand the clusters, and there's a lot less data that is need to be stored within the local cluster itself. And one of the goals of this entire kit is to no changes required from clients. Clients operate as it is today. They have pretty much no idea if the data is in local or in a remote storage. That is the idea. That is the goal that we are trying towards, and trying to kind of deliver that. Definitely, we do not have any API changes at all right now for the clients. So hopefully that kind of gives you introduction of Kafka at Uber, why we did choose Kafka tier storage, what are the promises of Kafka storage, Kafka tier storage. And with that, I'm going to toss it back to Satish, who will go much more in depth about the Kafka tier storage and all the interesting details that we have to work on. Satish?
Thanks, Harsha. Yeah, I'll give a brief introduction about the local storage in Kafka. As you all know, Kafka cluster contains several brokers, and each broker hosts several topic partition replicas, right? So each replica maintains a log, which is an append-only message store. And each log contains a sequence of log segments. As you can see here, there are 5 log segments. And the last one is called active log segment, which is not yet rolled. And the messages are currently kind of appended to that segment, right? So as you see, each segment contains all the messages. And along with the messages, we also maintain some indexes and states, right? So here we have time index, offset index, transaction index, and it also contains later epoch state. With the introduction of tiered storage, we are going to have local log segments as well as remote log segments, because some of these local log segments would have been copied to remote storage. Before we enable tier storage, you can see there are around 14 log segments for a specific topic partition, right? So with tier storage, we introduced a new config called local log retention. Okay, so that is like log retention, but it is meant for local storage. So you can configure based on like your use case, how long you want to keep the segments in local storage. It may be a few hours or few days based on your use case. So you can see there is one segment which is highlighted, which is 12th. So what that means here. So until the 12th segment, all these segments can be copied to remote storage. So the constraint here is that segments end offset should be less than or equal to log stable offset. So what that means is we want to copy only the segments containing the messages which have completed their transactions. So you can see here, there are remote log segments from 1st to 7th, and there are local log segments from 6 to 14. This is the local log segments earlier to 6, they're all deleted, right, based on the local log retention policy. Okay, let us take an example here, right? So you have local log segment, 7 segments. So until 6, they're all eligible to be copied. Tier storage subsystem kicks in and it started copying these segments one by one, right? For a specific replica. So 1, 2, 3 are copied, and 4 and 5 are also copied. And local segments, it added a couple of more, right? Now local retention kicked in here and it deleted 1 and 2. That is okay because we already copied 1 and 2 to the remote storage. So there can be one more case where let us say for some reason those segments are not yet copied to the remote storage, but they are considered to be eligible for cleanup based on the log retention. Even though a log retention, based on the log retention, they're valid for removal, the tiered storage subsystem doesn't allow them to be removed until those segments are copied to remote storage. Right. After some time, the complete log retention kicked in here, right, based on the configs. So it deleted the earliest log segments in the remote storage, which are 1 and 2, which are eligible for retention. They got deleted. Yeah, let me summarize what we have discussed about the log offset constraints. Okay, we have local log, right? It is a sequence of local log segments. We have remote log, which is a remote log sequence of remote log segments. So RX is the remote log start offset, which is effectively the complete log start offset, right? And we have RY, which is the remote log end offset, right? And for local log, we have LX, which is the local log start offset, log start offset of the local log, and LY, which is the log stable offset, and LZ is the local log and offset, which is actually the log and offset of the log. So here, the one main constraint here is RY should be always less than or equal to LY, which is the last stable offset, right? So there can be some common segments which are there in local log as well as the remote log. Okay, so let me briefly talk about the remote log segment metadata. So this is the main abstraction that we use to store the remote log segments and as well as identifying the remote log segments. So when we copy any local log segment to the remote log segment, right? So this is the metadata that we generate for those remote log segments, and each of those remote log segments are identified with a unique ID, which is remote log segment ID. Even when you are actually kind of creating or copying the same segment, right? Because the segment was failed in the earlier run, right? You're always going to create a new remote log segment ID. That means whatever segments that are going to store in the remote storage, they're always having unique ID. So along with this, we have all kinds of other metadata like segment start offset, end offset. These are inclusive offsets, right? And what is the state, which I'm going to talk about in next few seconds, and segment later epochs, right? So this is a map against the later epoch and the respective offset within this segment. Let us say there are some later transitions that have happened, right? Those are all kind of covered within this segment later epochs. With tiered storage, we have introduced a few abstractions here. The first one is Remote Storage Manager. It is a new interface that we have introduced, and it should be implemented by the user. So its responsibility is to talk to remote storage and provide APIs like copying, fetching, and deleting. So users can actually implement based on their remote storage like HDFS, S3, Azure, GCP, or any other cloud storage. The second abstraction that we introduced here is Remote Log Metadata Manager. So this is not mandatory to be implemented because we have one inbuilt implementation that comes along with the with Apache Kafka. So what it does is it maintains an index of all the remote log segment metadatas. It is the index about the metadata, not the data, right? And it is backed by the default implementation is backed by an internal topic. So the other internal abstraction is Remote Log Manager. This is completely responsible for handling all kinds of operations like copying, fetching, deleting by using Remote Storage Manager and Remote Log Metadata Manager. Tiered storage has three major parts in it. The first one is about copying the segments to the remote storage. And the second one is about fetching the segments from the remote storage. The third one is about enhancing the follower fetch protocol to provide log lineage across all the replicas, even for the remote log segments. Okay, let us start with the copying part, right? So as you can see here, we have also briefly described this earlier. Whatever log segment that is eligible for copying, so that is picked up by Remote Log Manager, And what it does is it actually creates a remote log segment metadata, right? And that contains a unique ID, and it stores that in remote log metadata manager. Once it is stored, then it starts copying the segment to the remote storage using the remote storage manager, right? So there is a specific remote log manager thread pool which does this, right? And as you can see here, the remote log segment metadata, it has few state transitions. These are very simple state transitions. They're mainly about copying and deleting operations, right? When we are copying, before copying, what we do is we set the remote log segment state as copy segment started, and then we copy the segment to the remote storage using the remote storage manager. Once it is considered to be successful, then we update the state in the remote log metadata manager saying copy segment finished, right? So there are similar states that are available for delete. So this gets kicked in whenever there is any retention related operations that are done, like whenever you want to delete a segment because its retention is kind of expand, right? So it starts with before it actually deletes from the remote storage, it updates the remote log segment metadata state with delete segment started. Then it deletes the particular segment in the remote storage. Once the deletion is considered as successful, it updates the state again with delete segment finished. Okay, let us go to the second part, which is about fetching the remote log segments. So let us take an example here. You have a local log, right, here, which is from 5th segment to the 10th segment. Earlier to 5th segment, 1 to 4, they are all deleted based on the local log retention policy, right? On the remote storage side, you have segments from starting from 3rd to 8th. 1 and 2 are deleted because of the complete log retention policy, right? When there is a fetch request that comes to the replica manager, if it is available within the local storage, it serves like the way it is now, right? Let us go to how it handles for the remote scenarios. So replica manager receives the fetch request, then it checks whether it is available in the local log. It is not available, then it gives it to the remote log manager. So whenever a fetch request is received, it has the offset, right? The fetch offset for which we need records for. So we need to find out which segment actually contains that offset, right? So it actually asks remote log metadata manager, okay, this is the topic partition, this is the offset, and the leader epoch. Give me the segment which contains this offset, right? So it gives the remote log segment metadata. Then remote log manager takes that remote log segment metadata and it gets the indexes based on offset or timestamp. It gets the index from the remote storage. From the index, it finds out the position within the segment, right? So it gets the position within the segment. Then remote log manager uses the remote storage manager API. Okay, this is the topic partition, right? And this is the remote log segment metadata. And I need the data starting from this position. Then remote storage manager serves that API giving a stream of bytes, and remote log manager actually reads them and builds the messages, batch of messages, and it returns to the replica manager. This is the overall remote log state machine, right? So we already talked about copying and deleting of the segments. There is one more aspect here. So whenever a particular partition is deleted, maybe because the topic was getting deleted, right? So in that case, any partition deletions, they don't those operations don't need to wait till all the segments of the partition, remote log segments of the partition to be deleted. So what controller does here is controller actually marks for that partition to be deleted, right? It updates that state in the remote log metadata manager. And once that call is successful, broker can consider that the partition is deleted. So remote log metadata manager asynchronously, it maintains that state and it start deleting that partition. What does that mean here? So it has to get all the segments, remote log segments within that for that partition, right? And it starts deleting all those segments. Once all those segments are deleted from the remote storage, then it updates the state for that partition as delete partition finished. So these state transitions are all audited in, stored in remote log metadata manager. And these can be actually kind of used as audits for remote log state transitions. These are very useful in debugging as well as get clarity on like what all kinds of state transitions happen for a specific segment or as well as for a specific partition. Let us look into remote storage manager interface that needs to be implemented by user for their own storage providers. So it's a very simple pluggable interface. The operations here include copying, fetching, and deleting. This interface doesn't need to understand any tiered storage or like Kafka level semantics. It is more like given an ID, this is the data, right? So you have to kind of copy and it should be kind of retrieved by using the same ID, which is remote log segment metadata. Same with the delete operation. So the caller gives the remote log segment metadata, you get the ID and delete the respective files or the data that was already stored earlier. So all the heavy lifting about the semantics is already done within the broker. The next one is remote log metadata manager. It doesn't need to be implemented by user. They can use the default inbuilt one. Or if they want to kind of use their own implementation for whatever reasons, they can still do it and plug it in with the broker. So what it really provides is whatever remote log segment metadata, right, that is created while storing the segments. So we need to build an index here based on leader epochs and offsets. So as I've shown earlier, remote log segment metadata, let me just show that to you here, right? Remote log segment metadata, it contains a unique ID and it contains other metadata, which is start offset, end offset, and segment leader epochs here, right? So let us go back here. So based on that information, that indexing needs to be done and the respective APIs need to be provided. So the API is like, give me the remote log segment for this topic partition and for this offset and the epoch, right? So based on the data that it has, you can index to give this information. There are other APIs like earliest log offset, highest log offset for a given topic partition and leader epoch.
The third major part of tiered storage is follower fetch. So we enhanced follower fetch protocol to support consistent log lineage across all replicas, even with tiered storage, including remote log segments. I'll give you a brief overview of this protocol here. As I mentioned earlier, leader replica is responsible for copying the segments to the remote storage. So it copies the segments to the remote storage and updates the respective remote log segment metadata in the remote log metadata manager, right? So whenever a follower tries to fetch a specific offset from leader, and if that offset is not available in local storage, but it is moved to a remote storage, it sends the respective response to the follower. Right. So follower now needs to build all the required state until the offset in its local storage. So it fetches all the auxiliary data from remote storage, and it builds the state locally in the follower. So once that is done, follower starts replicating the data that is there in the leader's local storage. So this is a very brief introduction, as I mentioned. So there is a detailed, exhaustive protocol mentioned in the CAPE covering several scenarios. So you can go through them and let us know in the community if you have any questions. This whole session is an introduction to tiered storage and its high-level architecture. We plan to have deep dive sessions in future about some of the critical aspects of tiered storage. This is a major collaboration in Apache Kafka community. We would like to thank Jun, Kaushik, Alex, Kamal, and several others in Apache Kafka community who have contributed with their feedback and suggestions on the kit. Special thanks to Jun for reviewing this kit thoroughly and providing valuable feedback and suggestions. Thank you all.